Hi everyone and welcome back. In the first part of this episode, we generated a simple Hello World shellcode based on the assembly code over here, which we assembled and linked into a binary from which we extracted the next section and got the raw assembly bytes. We then placed that as an array in a C code wrapper, but there was a problem when we ran it. If you remember from the last episode, our message was not printed. Why? Because the address of the memory block that was supposed to contain the message string did not contain anything actually. We can still see the address if we scroll a bit up in one of the previous listings. By the way, this situation we're describing is not specific at all to macOS. Let's go back and have another look at the assembly code. Notice here that the address of the message string is moved into RSI. The problem is this code is not position independent. What do I mean by this? Although when compiled it worked correctly, if we embed it into another application, it won't work. That address won't be correct relative to the rest of the code and won't contain the string. We need a way to obtain the address of the string relative to the current code that we're executing. This is very important. We need a relative address. Let's have a look at the second version of the code and see how to fix this. We will use a trick which is well known to reverse engineers and exploit writers. It works the same way on Windows or Linux. Let's understand this because it applies to more than printing simple messages. Okay, in the beginning of the main function, we start with a jump to a label that I've called here trick. This label simply calls another label, continue. The benefit of this scheme is that the call instruction will place the address of the next instruction on the stack. Very useful. The next code is just a sequence of bytes defined using db command as we've done before. Okay, going from the beginning, we start in the main function and jump. Then the call jumps to this label with a very nice side effect of the call. We will have on the stack the address of the string. Look at the first instruction after the jump, a pop instruction which gets the address of the string into RSI, exactly what we need. If we look back, we need the address of the string in the RSI register. We get the address of the string into RSI and the rest of the code is the same. In RAX register, we have the system call write number 4, then the number of bytes to write and so on. Everything else, this part of the code, is the same. As before, let's compile this and get the bytes corresponding to this new shellcode. Compile and link commands are here. Let's see if we can get the hello message this time. The binary we get directly from this second version of the shellcode should be working. This is expected. Next, let's obtain the disassembled bytes from the text section of our Hello version 2 binary. We will keep only the bytes and will remove the addresses. And replace all the spaces with /x to create a string of hex bytes. Alright, we have our shellcode. Let's plug it into the C code wrapper and check what's happening. The new shellcode is a bit larger, but there's only a small difference. It doesn't matter. Okay, a quick format. Then compile. Great! Notice that now we have the message printed. Next, let's examine the application in the LLDB debugger to see how that small change made the code position independent. Again, set a breakpoint in main function, run the application and continue until we reach the call to the shellcode. At this point, step into this call, SI, and notice we'll start with the jump. Look closely. Let's match the call instruction in the debugger with the one from our trick in the assembly code to the continue label. Notice we have some instructions after the call that don't make sense. Let's take their address and try to print them as a string. It's exactly our message, which the debugger interpreted as instructions. Why? And more about this in another video. Another thing, let's check what we'll have on the stack after we execute this call. Keep this address in mind, ending in 3F95. This time we'll do step instead of next instruction to enter the call. Here we have the pop instruction, which will get the value from the top of the stack into RSI. Let's watch the value of the register and see what goes there. Changes are highlighted in red. Easy to see. This is exactly the value we've seen before, ending in 3F95, which is the address of our string. Let's display the content from that location as string. The rest of the code is exactly what we've seen in the first part. Have fun in the debugger if you want. Double check that it works without the debugger. Before we end, let's quickly recap what we've done in this episode. We've seen a trick to get the address of a string independently from the current instruction pointer. The trick involved a jump, JMP, followed by a call and finally a pop instruction. First was a jump to a defined label, followed by a call to another label. The call would place the following address, in this case the string, on the stack ready to be popped. I hope you like this short but cool trick and you'll recognize it in your future reverse engineering work. Make sure to play with the code and debugger on your own. Thank you very much for watching and see you in the next episodes for macOS reverse engineering stuff. Cheers!